Okay, so today we're going to cover chapter 23. So in the last few chapters, we kind of have looked at different contexts for which we can do confidence intervals, hypothesis tests, these kind of things. And chapter 23 is sort of our last section that we'll be looking at. And actually, we'll just be looking at a hypothesis test in this chapter. No more confidence intervals, at least here. So sort of the motivation here for this set of methods from this chapter kind of connects to what we've done in chapter 20 and 21 with proportions. So you've seen this table a few times now. It's our favorite example of a two-way table. We have smoking habits and socioeconomic status. And in chapter 20 to 21, you can think about we could do confidence intervals or a hypothesis test for individual groups. We could estimate the proportion of all American adults, for example, who are upper class current smokers, or whatever you want to talk about there. We could also, in chapter 21, think about we could compare groups, right? We could compare the proportion of upper class folks who are current smokers with the proportion of middle class folks who are current smokers. You could do a number of groups there. So for each cell, you could calculate a p-hat and do a confidence interval or a test. But the point is that each of these things have more than two categories. So instead of just yes or no, we have three categories. We have current, former, never, upper, middle, lower. And so kind of thinking about how might we do a more general comparison of these two variables. So if we were to compare different pairs, like if we compare all the different pairs that we have up here, that would be sort of tedious and too much work. You'd have lots of tests, lots of p-values. And even if you did sort of a bunch of individual tests or pairwise tests, there would be no way to sort of say something about these two variables overall. And so that's what we're going to look at how to do in this class, how to do in this chapter. So sort of more broadly, kind of going beyond what we did in chapter 20 and 21, where we looked at specific categories. Now we want to say something like, answer a question like, is there a relationship between the two categorical variables sort of overall? So instead of just comparing individual categories or individual groups, now we're going to say something about these variables overall. And we're going to use what we've learned before to kind of segue into the methods for this chapter. Okay, so a quick reminder of what we have here being a two-way table. Remember that a two-way table is a way of displaying two categorical variables, right? We have one on the column on the left and one on the row on the top, and then we can kind of organize our data. If we have a sample of people, we can cross-classify them and put them in the right places. So in our example here, again, the question that we want to ask with our two-way table of smoking habits and socioeconomic status, we want to ask if there's an association between these two things. So kind of formally, more formally say what we've done already, to answer the question, is there remember, if that's our question, is there association between these two variables? You might remember back to chapter 10 and 12 when we looked at probability. We sort of were getting at this idea of is there an association between these two things? So what we did there was we identified that there could be an association between these two variables based on some conditional probabilities. So again, the probability of, here's your favorite notation, the probability of being a current smoker given upper class. And here we have the probability of being a current smoker given the lower class. And so those two numbers are not the same, right? So what we can see from these two probabilities is that your chance of being a current smoker, the probability that you're a current smoker, is different based on what socioeconomic status you're in. So that you would think, if something about my socioeconomic status influences my smoking behavior, thinking about that would be some sort of an association, right? There maybe is a relationship here. So that's That's one way to do it. And we could also use an independence argument. Another way we talked about this. Remember that if the probability of A given B equals the probability of A, then we have independence. So what we can see here is that the probability of being a current smoker given being in the upper class, again here is the 51 out of 211, or 20.24. Whereas if we look at the probability of being a current smoker, that is 116 out of 356, which is 0.326. And of course these things are not equal to each other. So that's another way of saying that. So if these two things were, if they were equal, then we would have independence. Since they're not equal, that's a way to show us that there's some sort of a relationship going on here. So this is just to remind you of what we did before, to kind of informally say, is there a relationship between these two variables? We used this idea of conditional and probability. So the other thing we could do, again back in chapter 21, what we could do is look at and find that there is a significant difference between the smoking rates of persons from the upper class and those from the lower class. So same kind of idea. If we define P sub u to be the proportion of upper class current smokers, so looking at current smokers here, and P sub L to be the proportion of lower class current smokers, we could do a confidence interval for that difference. That's what we would do in chapter 21, and we can find that thing is 0.1034 to 0.3366. And so why does that confidence interval by itself just sort of immediately tell me that there is a difference between these two groups? Let's see if you've done your chapter 21 homework already. So if this is my confidence interval for the difference between the lower and upper class current smokers, how does that confidence interval by itself tell me that there is a significant difference here? Yeah. Yeah, right. So the confidence interval does not include 0, so you're not saying that difference could possibly be 0. So the groups are different because the interval does not include 0. So that is another way of telling us that if we have something different going on in our groups here, maybe there is some sort of association between these two variables. Again, just to kind of remind you what we have done and how that kind of relates to what we're looking at here. But now again, kind of restating this again, what we want to do is we want to look at these two variables overall. So before we've just looked at pairs of variables or whatnot. And again, we have this problem of multiple comparisons. There's sort of this theoretical thing we didn't spend a whole lot of time talking about. But when you have when you're doing lots of comparisons, so if I'm comparing each of my groups, if I compared cell 1 with cell 2 and cell 1 with cell 3 in that table and did a bunch of those things, that's kind of a bad. What it says here is it compromises the integrity. So you don't want to do the lots and lots of tests because that's going to be a big mess. So sort of the convention here is that we want to do an overall test of there being evidence of some relationship between these variables, and then you can kind of go on to sort of do a follow-up analysis to see which parameters or which groups are actually different and by how much. Okay, so with this goal in mind, I guess maybe I'll quickly also add that we're going to focus on the overall test. So we're not going to talk a lot about that second thing. We'll sort of do informal things, or I'll leave that to a future statistics class if you want to kind of know how to say more about this type of data. Questions, comments you guys can think of so far? So I guess all that was just kind of, here's our problem. We want to talk about an association between these two variables. Think about what we've already done, how that relates to this question. And now we want to take it a step farther to do this overall comparison. So again, we're going to do a hypothesis test here. So we need to figure out what hypotheses are we interested in testing. So as usual, we will have our null hypothesis and our alternative hypothesis. And what we're going to look at in this chapter, again, what we want to see if there's an association between these two variables, right? So what we're interested in saying, as usual, is our alternative hypothesis, which says that there is an association and we can say what two variables we're looking at here. So here we're looking at smoking habits and socioeconomic status. So remember, our convention is to sort of whatever question we're interested in answering, that goes in our alternative hypothesis. So here we want to see, is there an association? And so the alternative says that there is an association. You can say it either way is fine. And then anybody want to guess what the null hypothesis is going to be? Again, remember the null is always sort of the opposite of what you want to show. So what's my null hypothesis going to be here? Exactly right. Thank you, Lisa. There is not an association between these two things. Exactly. So our alternative hypothesis, kind of what we want to show is, is there a relationship, or saying that there is a relationship or an association. And then the null hypothesis, sort of the opposite of that, is going to say that there is not an association between smoking habits and SES, or whatever two variables you're looking at. So now this is a little different than what we've seen our hypotheses to be before. Usually it's like mu equals something, P1 equals P2. There's no more symbols in there. And that kind of, it's not necessarily a problem, but just sort of to note that this is a very different type of test than we've done before. And just pointing out that our alternative hypothesis is, we don't have like a one-sided or a two-sided or a one-tailed or two-tailed test anymore. What we'll say is that it's quote, many-sided. And that's because the alternative hypothesis doesn't say what the relationship is between those two variables. It's just saying that there is an association. We're not saying what that association is. That's kind of where we take it a step farther and do the follow-up things. And so that's just to point out this is a very, very different type of a hypothesis test than we've seen before. All right, so the hypotheses are different, but the strategy is exactly the same. When we want to as we think about how we can do this hypothesis test, what we'll start out saying is that we first want to assume that the null hypothesis is true. So just like before, we assume the null hypothesis is true, we're going to do the same thing here. And so what that means is that what the null hypothesis says is that there is no relationship between the two variables. And so kind of another way of thinking about no relationship or no association, that means that they are independent. So we've talked a lot about independence now, and we're kind of coming back to that more here. Just the idea that no relationship between two variables sort of means the same thing as them being independent. So we want to think about how this applies in our example here. So again, coming back to chapter 12 material, if you remember all the way back to that. maybe chapter 10 actually, we had that if we have two events, A and B, if they are independent, then the probability of A and B is equal to the probability of A times the probability of B. So similarly here, if we have two categorical variables, variables 1 and 2, or if you want to keep those labeled A and B, categorical variable A and categorical variable B, if those two variables are independent, then if there's two outcomes, we'll say R and C, that could be like upper class and former smoker or something like that, then the probability of being in both of those groups, or in being just a single cell of that thing, is equal to the probability of the first thing times the probability of the second thing. So sort of the same idea. We'll kind of think about how this translates into our example here. So yes, so it's kind of saying the same thing. So for a two-way table, the probability of having an outcome of R and C. So this is a single cell. So the probability of falling into a single cell. So for example, being lower class SES and a former smoker or something like that, is simply equal to the probability of the marginal probability of observing that first thing times the marginal probability of observing the second thing. So probability of being lower SES and being a former smoker, kind of those two probabilities, you can multiply them together to get the probability of having both of them, if they are independent. So let's think about how we can apply this to our example here. So there at the top is our table again. We can do marginal distributions. Marginal just involves the bottom row and the far column there. So we have our first we have SES. We can look at upper, middle, and lower class and think about the probability of being in each of those groups marginally. Same for our smoking habits. And now we can fill in kind of our probabilities of falling into each of these cells here. So I'm just going to focus on this first column to kind of show you where these numbers come from. So if I want the probability of being a upper class person who is and a current smoker, so having being upper class and being a current smoker, again, independence tells me that I take the probability of being a current smoker and multiply that times the probability of being in the upper class. So how I can fill this in is I can take my probability of being upper class, so 211 out of 356, and multiply that times probability of being a current smoker, so 116 out of 356, and that's going to be about 0.19331. So again, if I have independence going on here, the probability of being in that first cell is going to be equal to the sort of the probability of the whole row times the probability of the whole column. And I can do that for the middle class current smokers as well. I can take the row total, so 52 out of 356 times 116 out of 356. And that's going to be 0.0476. And then for the last one, I can do the same thing. I have 93 out of 356 for my lower class folks times the current smokers, 116 out of 356, and I'll get 0.0851. And then I'm not going to take time to calculate every single one of these. You have the tables are in your notes. But we could do this for each cell in the table, right? So we did it for the first column. We do the same thing for the second and the third column. To find if these two variables really are independent, sort of find your probabilities of falling into each cell. So if they really are independent, the probability of being a lower class and former smoker is 0.1035, similarly for the other things on there. Everybody okay with what we're doing here? Kind of if these two things really are independent, this is what would be going on. So just to kind of reiterate what we did to find the probability being in the row R and the column C. So R and C, we took the row total from that row and the column total from that row and multiplied those probabilities, those marginal probabilities together. So that led us to this table where we had a bunch of probabilities floating around in there. But again, kind of thinking back to the original table, we don't have probabilities in there. We have numbers of people, right? We have the counts that are in each group, the number of people that are in each group. So thinking about what would we expect this table to look like if we had 100 subjects. So again, thinking about if we had 100 people, how would we expect them to be kind of spread around on this table? So keeping in mind so what we can do to look at that is simply just multiply every number in that table by 100. So on your marginal probabilities, we had the current smokers was 32.6%. So out of 100 people, that's going to be 32.6 people. And we could do the same thing for all of these things. So we had up here we had 0.1931 times 100. That would be 19.31. Just kind of going through this first row again real quick. We had 0.476. And finally we had 0.0851. So again, if I have a probability, if I have 100 people, and 19.31% of them are upper class and current smokers, that just means that I'll have 19.31 people in that group. And I can do that for the whole table. So what I've done is I've just taken that previous table I had up there with all the probabilities in it, and multiplied every number in that thing by 100. So again, the idea here is that if these two things really are independent, and I have 100 people, this is kind of how many I would expect to be in each category, each group. But the idea, of course, is that we had 356 people to start with, so why would we compare 100 people? We can do the same thing for our 356 people. Go back to that probability table and just multiply everything by 356, and that will give us kind of the very, very similar thing. So before it was... Now we're multiplying times 356, and that'll give us 68.75 people in that first cell. 0.0476 times 356. And finally, so I'm just taking, again, going back to that probability table and multiplying everything in there by 356. So again, if I have 19% of my people who are upper class and current smokers, if I now have 356 people, that means that I'll have 19% of that is 68.75. And again, I can do that for the whole table. So I can calculate sort of my how many people I would expect to be in each group. If I have 356 total people, same as we actually do in the table here. And the kind of the cool thing I think that happens here is, and maybe it's obvious, but that the row and the column totals do again add up correctly. So that's kind of a cool thing, I think. All right, so where are we going, Mark? Here, right? The key idea here is that if I really do have 356 people, and if these variables really are independent, so if SES really is independent of your smoking habits, then if I have 356 people, this is kind of how many I will have in each group. So that's how these 356 people would be distributed across this table if these two things really are completely independent. It's kind of what I'm getting at here. Questions or comments you guys can think of at this point? It's quiet in here today. Okay, so the key thing here is that this is our expected cell count that we would get if we assume independence here. So kind of thinking about the formulas that we've used here, our expected cell count is sort of the marginal probability of the first of whatever row we're in times the marginal probability of whatever column we're in, and then we multiply that times the total number of things we had in the table. And so we can kind of simplify that if we're looking at it this way. Our expected count is going to be the total from the row times the total from the column and divided by the total from the table. So this is kind of a simplification of that top row there. Okay, so that's how we're going to figure out what our expected cell counts are. Again, this is our expected if we have independence. It's a big if there. Okay, so again, kind of where are we going here now? Again, we have our hypotheses, so we've thought about what our null and our alternative hypotheses are. Our goal now, you could maybe think about where we're going, is how we would test those things. Is we want to determine if what we observed, so the numbers that we actually observed. I took these 356 people and put them in a two-way table. I want to see if those observed values are significantly different from the expected, what I would expect those cell counts to be. So I don't know if that sounds familiar. We're kind of comparing something of what we observed with what we would expect, and that's kind of how we've been doing hypothesis tests all along. We assume that the true mean is some value, and then we compare that with what we actually observed, or we assume the true proportion is some value, and we compare that with what we actually observed. So kind of think about where we're going. We need a test statistic to kind of put all this together, and we need to figure out how to find our p-values. And so that leads us to this idea of this thing called the chi-square test statistic. So maybe some of you have heard of this before. The X-looking Greek letter is again chi, so the H is sort of a silent H, I guess. So the chi-square statistic is a measure of how far the observed counts in this 2A table are from the expected counts. So this is our way of comparing, kind of like before, sort of how far away from what we'd expect under our null hypothesis, how far away the actual data we have are from there. So again, we're calling this thing chi-squared. We're going to sum over all cells in the table. We're going to take the observed count, so what we actually see, what we actually observe. We're going to subtract off the expected count and square that, and then we're going to divide that by the expected count. And actually, so in a class that I had one time, the professor wrote it this way. So we're going to write the sum of the observed count, so O sub I minus the expected count from the ith cell, and square it and divide it by the expected count. That's another way of looking at it. And I guess it's kind of coming backwards, but there's a little EI, I there. If that helps you to remember this thing. Or OI, EI. It's a little backwards there, I guess. So this is what our test statistic is going to be in this chapter. So it's very different again than what we've used before here. All right, so let's practice doing this here. So again, here's our table, and now I've included both the observed counts and the expected counts in here. So in each cell, I have the observed counts and then the expected counts there in parentheses. And again, that's in your notes. And so let's think about how we can calculate these things. And just some terminology here for you is when I calculate this observed minus expected squared over expected for a single cell, I'm calling that the cell's contribution to the chi-squared statistic. So I'm adding up a bunch of these contributions from each of the cells. Remember, that's my whole test statistic. Okay, so let's think about calculating a few of these. So my upper and current, the observed. So remember, I'm taking observed minus expected squared over the expected. So the upper and current, I had I observed 51 people, and I expected there to be 68.75 in there. And I'm going to divide that by the expected, so 68.75. So that's negative 17.75 squared over 68.75. And that's going to be 4.58. So I'm just taking what I observed. I observed there to actually be 51 upper class current smokers, subtracting off what I expect there, which was 68.75. Square that divided by the expected counts. And I can do that. I'm not organized my space here very well. But for the middle and current group, I can take the observed account, which was 22, subtract off what I expected, which was 16.94. Square that divided by 16.94. Do a similar calculation, and I get that to be 1.51. And finally, for the lower class current smokers, I'll take the observed, which was 43, minus 30.3, squared divided by 30.3, which is 5.32. So again, this is what we're doing here is we're calculating the contributions of each one of these cells to the overall thing here. All right, so time for you guys to get involved here. What do you notice about these three contributions that I've calculated? 4.58, 1.51, 5.32. Thinking about sort of what do you notice about those things? Very basic stuff. They're all positive. Thank you. Yes, that's the obvious one. They are all positive. So that's the main thing to take away. But I guess also just note that I guess the contribution for the lower class current, for the lower cell is the largest, and then we could also say the middle current group was the smallest. But the important thing to note is that they are all positive. So I do this for my whole table. I add them all up. I'm going to get something that is also positive. I can't get something negative for my test statistic there. So if you happen to be doing that by hand and you ever get something negative, that's a bad thing. Okay, so again, I can calculate the contributions for all of my cells, and then I can use those to figure out what my test statistic is here, my chi-square statistic again, it's the sum of all of my observed counts minus expected squared divided by the expected. And so I can add up those ones that I already did. So I came up with a 4.58, and the middle class current cell was 1.51, and the last one was 5.32. I'm gonna be lazy and put some dots in there and tell you if I calculated all of them and added them all up, I would get 18.50. So I'm not totally cheating here. Again, we're not gonna have you do these all by hand, because that would be tedious and annoying. So that's the good news here. But anyway, if I were to calculate them all for each one of my cells there, I did it for just the first 3. If I did it for the other 6, I could add them all up and get 18.50. And just to prove to you, here I can show you my table again. Now what's in here is the contribution. So there in our first column, you can see what we calculated, and there they are for the other cells. And so, I mean, you don't have to organize these things into a table, but it does kind of show you what categories or combination of categories that are sort of showing you that having the biggest numbers in there, or sort of shows you which ones are farthest from what we expected. So it shows you where the observed is farthest from the expected. So again, that would be right here, and that's the one that's the very farthest away, and then the middle class former smokers is close. We got really close there to what we would expect, and then think about that for the whole table. So in your notes, Dr. Baker put a note that you can. I don't know if you guys like using Excel. You can use that as a way to do this too. But again, we're going to be using technology. Is kind of where we're going with this thing. So you might be wondering, well, where are our conditions, right? Don't you just feel like you need to be checking some conditions in here? So there are some conditions that we need to check for this test, and kind of like we did in our hypothesis test for proportions. We looked at the expected number of successes and failures. Here we want to use the expected counts to check our conditions. And so again, we definitely want to have a random sample. That one's still here, but sort of the small enough and the large enough are now gone, and we just have this thing here. So we can safely use this test when we have again no more than 20% of the expected counts are less than 5, and making sure that all the individual expected counts are at least 1. So make sure we have no zeros in the table. So this is the formal condition, but if all expected counts are bigger than or equal to 5, we're good to go. Good to go. So number 1, just make sure that number 1 allows us to have some of those expected counts that are less than 5, but again, if you're looking at the expected counts and they're all bigger than 5, then you're all set. You're good to go. So again, these conditions are actually a little easier to satisfy than some of the other ones we've seen. So have we satisfied our conditions here for this example? Well, yes, of course we have. The smallest expected count is 14.45, I think, which is bigger than 5, and we have a and we do have that random sample that was stated kind of in the first part of your notes. Assume that we have that this table is a random sample from all adults or something like that. So because our smallest expected count is bigger than 5, we're all set here. Questions, comments from you guys? Feeling okay still? Okay, so again, coming back to this idea that we are going to use technology, it's good to kind of, again, the main point of this class as I see it is to kind of understand how the procedure works, but then not waste lots of time doing everything by hand. So again, we're going to be using jump for this kind of a thing. And if you put this information into jump, sort of the default thing it spits out is this kind of funky looking table. But we have our current, former, and people who have never smoked before, as well as our lower, middle, and upper. And again, just maybe a note here that there does appear to be an association. So if there were no association, I think the rows would all have the same spacing there. It wouldn't be kind of chopped up like that. I haven't really used a table like this before, but just a point that jump will give you this. But more importantly, jump will give you this table. So this is kind of like the thing that we spent a lot of time calculating already. So when you put the information in, I'm going to note that jump will alphabetize the levels for each categorical variable. So over here we have lower, middle, upper instead of the other way around, and current, former, never. And we still have our totals are in the margins, but now each cell contains 3 things. So that each cell contains the observed count, so the number that you actually entered in. It also does the expected count for you, and it also calculates the contribution to the chi-square statistic. So the default does not give you all 3 of those things, but you are able to find those things by clicking on the little red arrow. I think it's one of those kind of things. So maybe just a quick note about the exam. This material will be showing up on the exam, but what we'll give you on the exam is output from jump, which we'll look at in a second here. And you might have to calculate some expected counts or some contributions or something like that, kind of like we've done already. But you'll be using the technology output on the exam. Okay, so just about to finish up for today. Kind of thinking about more formally putting together what this test is saying. Again, we want to use this thing to test the null hypothesis that there is no relationship between these 2 variables. And then again, we had wanted to make sure our counts were in the right shape, and then we want to make sure we have our random samples. So this is stating this a little bit more formally. So this is my So I either want to have independent samples from each category in one of my groups, or just a single simple random sample with sort of cross-classified people. So again, thinking about now what we have, we've said what our hypotheses are, we've thought about what our conditions are, and we have our formula for our test statistic. And so the next step, of course, is to figure out how to calculate p-values. And to do that, we need to know what the distribution of this thing is going to be. So maybe this will be a good place to finish up. But just to kind of introduce this thing called this new distribution that we're looking at, it's called the chi-square distribution. So again, just like the normal distributions or the t distributions or any of those things, it's a family of distributions that takes on only positive values and is going to be skewed to the right. So this is kind of a different thing. For our normal distribution and our t distribution, we could take on any value on there, positive or negative, and it was symmetric and all those nice things. The chi-square distribution is going to look a little bit different, but sort of like the t distribution, it's going to depend on its degrees of freedom. So that's, again, something that we're going to have to calculate. And so how do I find out what my degrees of freedom are? Well, if I have a 2A table with lowercase r number of rows and the lowercase c number of columns, my degrees of freedom is going to be the rows minus 1 times the number of columns minus 1. And then the p-value, again, remember we don't have like a one-sided or a two-sided p-value anymore. the p-value is always going to be the area under that curve out to the right of the test statistic that you get. So you're always going to be looking for that sort of that tail probability off to the right. And to show you a picture here, here's what 3 of these things look like. These are the blue curves represent different chi-square distributions based on what the degrees of freedom are. So in the kind of that farthest one to the left, we have 1 degree of freedom, and then we have a 4 and 8. So you can kind of see it's always bigger than 0. It has that right skewed pattern, and the degrees of freedom kind of determine sort of how flattened out it is. And so just real quick, let's calculate what our degrees of freedom are for this example that we've been looking at. Again, we have 3 rows and also 3 columns. So our degrees of freedom is going to be 3 minus 1 times 3 minus 1, or 4. So for this example, we're going to have 4 degrees of freedom. Questions, comments on the chi-square distribution? Again, that's sort of the kind of like the t and the z were before. This is the distribution of our test statistic that we can use to find p-values. So looks a little different now, but same ideas will be holding. All right. Well, since it's the last week of class, I'm going to go ahead and call it quits. Thank you guys so much for being here. Have a good rest of the day, and we'll see you on Friday.